A colossal sphere of gas and dust swirls in the emptiness of space. This is not just a nebula, it is a cosmic construction site where planets are born. For decades, we thought we understood this process, a slow and steady build-up from the ground up, but a revolutionary idea shatters that classic story. It is called disk Instability Top-Down Giant Formation, and it suggests planets like Jupiter can form in a cosmic blink, a fast food-style feast compared to the slow-cooked core accretion method. By the end of this exploration, you will understand how our entire picture of planetary birth is being rewritten. We will uncover how a disk of gas can tear itself apart to create a giant world, and why this could be the key to finding alien solar systems unlike anything we ever imagined. What does it mean for a planet to be born not from the bottom up, but from the top down for generations? The story of how a planet is born has followed a very specific script. It begins with tiny particles of dust floating in a disk around a young star. These microscopic specks bump into each other, sticking together with static electricity, slowly growing from dust to pebbles, then from pebbles to boulders. This is the core accretion model, a bottom-up construction project of cosmic proportions. Think of it like rolling a giant snowball across a snowy field. You start with a tiny handful of snow, and as you push it along, it gathers more and more material, layer by layer, until you have a massive sphere. In space, once this rocky core grows large enough, its gravity becomes strong enough to start pulling in the surrounding hydrogen and helium gas. It builds an entire world from the ground up. The problem is time. This entire elegant process is incredibly slow, often requiring several million years to form a giant planet. This creates a major puzzle when we look at real solar systems. We find gas giants, planets like Jupiter, orbiting astonishingly far from their host stars in regions where the disk material is sparse. According to the slow and steady core accretion model, there just would not be enough time or material out there for a planet to gather itself together before the young star's radiation blows the gas disk away entirely. The classic story leaves giant planets in the outer suburbs with no way to explain their existence. This glaring gap in our understanding is exactly what forced scientists to consider a much faster, more dramatic path to planethood. The clock is ticking from the very beginning. A newborn star's planet-forming disk, that swirling buffet of gas and dust, is a temporary feast. The star itself is a violent toddler, unleashing fierce winds and intense radiation that relentlessly blow the disk material away into the void of space. This entire cosmic construction site has a very short shelf life, perhaps only 2 to 5 million years. You have to build your planets before the all-you-can-eat gas buffet closes for good. This is the core accretion model's greatest weakness, the timescale problem. Building a gas giant from a tiny speck of dust is a painfully slow process. First, you need to patiently assemble a rocky core 10 times more massive than Earth, which itself takes ages. Only then can that core's gravity begin to pull in the vast atmosphere of hydrogen and helium that defines a gas giant. But by the time that rocky seed is finally ready, the gas it needs to feed on is often already gone, blown away by the young star. The process simply runs out of fuel before the main event can even begin. This timing crisis becomes even more baffling when we look at the planets we are actually finding. Our telescopes, especially the James Webb Space Telescope, are now directly photographing alien worlds that defy the old rules. We see super Jupiters, colossal gas giants many times more massive than our own Jupiter, orbiting incredibly far from their stars. In these distant, frozen suburbs of a solar system, the disk material is incredibly sparse. For core accretion to work there, the process would have to start with almost no building blocks and then somehow race against a clock that is ticking even faster due to the weak gravity in those outer regions. It is like trying to build a metropolis in the middle of an empty desert with a deadline of just a few years. It just does not add up. These distant giants are the key piece of evidence that shattered the old story. Their very existence points to a different, far more dramatic birth. They are the cosmic mysteries that forced astronomers to ask a revolutionary question. What if these planets were not built slowly, piece by piece, but were instead born in a single, violent event? This is where the maverick theory enters the stage, turning the entire story of planet formation on its head. Disk instability is not a slow, piece-by-piece construction. It is a top-down process, a sudden and dramatic collapse. Forget the patient snowball rolling downhill. Picture instead a massive, swirling disk of gas and dust orbiting a young star. This disk is incredibly dense and relatively cool. Under these specific conditions, something remarkable happens. The disk's own gravity, the collective pull of all that gas and dust, can overpower the forces that are trying to hold it together. The disk becomes gravitationally unstable. It can no longer maintain its smooth, uniform shape. Think of it like spinning a large, wet blob of pizza dough. If you spin it too fast, or if the blob is simply too big and heavy, it does not stay in one piece. It tears itself apart, collapsing into several smaller, independent blobs. In the protoplanetary disk, this is exactly what occurs. The entire structure fragments directly into self-gravitating clumps. Each of these collapsing pockets of gas and dust, under the immense crush of its own weight, can ignite the birth of a gas giant planet right then and there. There is no need to wait for a rocky core to form first. The planet is born fully formed from a large-scale structural failure of the disk itself. The most staggering part of this process is its breathtaking speed. While core accretion plods along for millions of years, disk instability can forge a giant world in just a few thousand orbits. Around a young star, that is a mere blink of an eye, a cosmic instant. This lightning-fast mechanism solves the timescale problem perfectly. It explains how giant planets can appear in the distant, sparse reaches of a solar system, building themselves from the top down before the star's radiation has any chance to blow their gaseous raw materials away. So what exactly does it take to push a placid disk of gas over the edge into a cosmic demolition derby? The recipe for this top-down chaos hinges on a delicate balance between two opposing forces, a balance captured by a single, powerful number known as the Toomre Q parameter. In simple terms, this number tells us whether a disk is stable or primed for collapse, and it all comes down to a cosmic tug of war. On one side, you have gravity, the relentless force that pulls the gas inward, trying to make it clump together. On the other side, you have two forces fighting against this collapse: pressure from the heat of the gas itself, which pushes outward, and the centrifugal force from the disk's rapid rotation, which tries to fling the material apart. For instability to win, for gravity to finally overcome its rivals, the disk must be both very massive and very cool. A massive disk means there is a lot of material, giving gravity a stronger hand to play. A cool disk means the internal pressure is low, offering less resistance to gravity's pull. When these two conditions are met, the Toomre Q parameter dips below a critical value and the entire system becomes gravitationally unstable. We can see this dramatic transition play out in stunning mathematical simulations. At first, the disk is a smooth, featureless ring, but as the conditions become unstable, it doesn't just randomly clump. Instead, beautiful, dense spiral arms begin to form, like the patterns in a spinning pinwheel galaxy. These arms are not just for show, they are the engines of planet formation. They act as cosmic traffic jams, concentrating vast amounts of gas and dust into narrow lanes. Within these spirals, the density soars and gravity's grip becomes overwhelming. The arms then begin to fragment, pinching off into individual, self-gravitating clumps that will eventually contract into protoplanets. It is a breathtaking chain of events, from serene disk to spiral whirlpool to the birth of new worlds. Several key factors determine whether a young solar system will take this fast-track path. The mass of the central star is crucial. A more massive star generally has a more massive disk orbiting it, providing more raw material for instability. The temperature of the disk is equally vital, as a cooler disk has weaker thermal pressure, making it easier for gravity to cause a collapse. Finally, there is the rate of accretion, the constant rain of new material falling onto the disk from the surrounding nebula. A high accretion rate can suddenly dump a huge amount of mass into the disk, pushing it past its breaking point and triggering the instability almost instantly. This rapid formation mechanism is not just a theoretical idea. It is a direct and elegant solution to the puzzle of those distant, lonely giants, forged in a violent instant before their celestial nursery could fade away. The transformation of a stable disk into a chaotic nursery of planets is a spectacle best witnessed through the eyes of a supercomputer. Sophisticated simulations reveal the process not as a random clumping, but as an elegant, almost inevitable dance of physics. The first sign of trouble is the emergence of beautiful, shimmering spiral arms. These are not mere patterns painted on the disk. They are deep, dense waves of material, cosmic traffic jams where gas and dust are forced together. They look strikingly similar to the grand spiral arms of a galaxy, but on a much smaller, more frantic scale. Within these swirling arms, the density of material skyrockets. The collective gravity within each spiral wave becomes immense, turning it into a self-contained gravitational trap that pulls in even more surrounding gas. This is the point of no return. The spiral arm, now overloaded with mass, can no longer hold its elegant, elongated shape. It begins to buckle and pinch under its own weight. You can watch it happen in a simulated time-lapse, a dynamic and violent ballet. A section of the spiral arm, thick with promise, starts to contract. It pulls away from the larger structure, its own gravity now dominant, sealing itself off from the surrounding disk. In a final, decisive moment, it fragments, pinching off into a distinct, glowing clump. This newly born object is no longer just a wave in the disk. It is a bound entity, a protoplanet. It has its own center of gravity and a fierce destiny, destined to cool, contract, and become a full-fledged gas giant, all born from the top-down collapse of its own celestial cradle. The moment a spiral arm fragments, a new cosmic object is born, but it is far from a finished planet. This newborn clump enters the universe as a vast, diffuse, and surprisingly hot ball of gas. It is a puffy protoplanet, a temporary structure bloated with the heat of its own violent birth. Held together only by its self-gravity, this initial state is incredibly fragile. The clump's first order of business is simply to survive. It begins a long process of gravitational contraction, a slow and steady squeezing as it radiates its intense heat away into the cold of space. Over thousands of years, this relentless compression causes the clump to shrink, becoming denser, hotter at its center, and more defined. It is maturing from a chaotic wisp of gas into a coherent world. But what about the dust? Throughout this entire process, the clump is not just pure gas. It is also filled with countless microscopic dust grains that were caught up in the collapse. As the gas churns and cools, these solid particles begin to behave like a fine mist settling on a still pond. Drawn by gravity, they drift slowly inward, sinking through the thick atmosphere toward the very center of the protoplanet. Over immense spans of time, this rain of dust can accumulate into a dense, solid core. This presents a fascinating twist. A planet born from disk instability could still end up with a rocky core at its heart. The critical difference is one of cause and effect. In the core accretion model, the solid core comes first and builds the planet. In disk instability, the planet forms first, and the core is a later addition, a consequence of the instability, not its cause. This single distinction rewrites the origin story for entire classes of planets. Not every clump is destined for a long life, however. The early solar system is a chaotic and dangerous nursery. Some of these newborn gas giants survive, continuing to contract and cool until they become the stable, majestic planets like Jupiter we recognize, but others meet a far more dramatic end. A clump that forms too close to its host star can be torn apart by immense tidal forces, its gas shredded and scattered back into the disk. Other clumps might begin a slow migration inward, spiraling toward their star to be consumed, or they could be violently flung out of the system entirely by gravitational interactions with their siblings. This cosmic sorting, a relentless process of creation and destruction, is what ultimately sculpts the incredible diversity of planetary systems we see across the galaxy, from tightly packed giants to lonely wanderers adrift in the dark. This scientific clash is far from settled, creating one of the most dynamic debates in modern astronomy. On one side, you have the classic core accretion model, a theory with the comfortable weight of explaining our own cosmic backyard. Its proponents point to the elegant order of our solar system. This bottom-up process perfectly accounts for the clear division between the small, rocky inner planets like Earth and Mars and the gas giants orbiting further out. It explains why our system is not filled with countless giant worlds, as core accretion is a slow, meticulous process that naturally limits the number of behemoths that can form. The theory's greatest strength is its demonstrable success in describing how trillions of rocky planets across the galaxy could be built from the dust up, providing a plausible origin for worlds like our own. For many, the familiar, step-by-step nature of core accretion feels like a complete and proven story. Yet, for all its successes, the classic model faces an undeniable crisis when it looks beyond our sun. This is where disk instability advocates present their compelling case. They argue that our solar system, while precious to us, might be the exception rather than the rule. How else, they ask, can we explain the existence of those colossal planets photographed by our telescopes, worlds 10 times the mass of Jupiter, orbiting so far from their star that core accretion seems impossible? Their theory provides the perfect solution, a fast track to planet formation that operates on a timescale the old model cannot match. It is the only mechanism that seems capable of building giants in the sparse, frozen outskirts of a stellar system before the raw material vanishes. The most fascinating possibility, however, is that this is not a battle with a single winner. We do not necessarily have to choose one theory and discard the other. The universe has never been that simple. Instead, both processes could be happening simultaneously, each dominant in its own specific environment. Imagine a single, massive protoplanetary disk swirling around a young star. Close to the star, where the disk is hotter and the material is denser with rock and metal, the conditions might be perfect for the slow, steady grind of core accretion to build rocky planets. But further out, in the cold, massive outer regions of that very same disk, the conditions could be just right for disk instability to take over, rapidly forging giant planets from collapsing spiral arms. Our own solar system might be a product of core accretion simply because our sun's protoplanetary disk was not massive or cool enough to cross the threshold into instability. Another system, born from a heavier, colder disk, could be filled with giants born from the top down. This dual pathway understanding of planet formation opens up a universe of incredible diversity, where the fate of a solar system is written in the initial mass and temperature of its birth cloud. The search is now on for the definitive evidence that will show us which process forged which worlds. The hunt for proof now moves from supercomputer simulations to the cold, thin air of the Chilean desert. Here, at an altitude of over 5,000 meters, the Atacama Large Millimeter Array, known as ALMA, turns its 66 radio antennas toward the sky. This telescope does not see visible light. It peers into the universe at millimeter wavelengths, allowing it to cut through the obscuring dust of protoplanetary disks and see their underlying structure with breathtaking clarity. ALMA images are not just pretty pictures, they are forensic snapshots of planet formation in action. and they have delivered some of the most compelling hints that disk instability is a real cosmic process. One of the most stunning examples is a young star system named AB Aurigae, located about 500 light-years away. When ALMA focused on this system, it revealed a protoplanetary disk that looks exactly like a simulation of gravitational instability come to life. The disk is not smooth or featureless. It is etched with two distinct, bright spiral arms, cosmic whirlpools of gas and dust that coil tightly around the infant star. These are not the gentle spirals of a distant galaxy. They are the dense, gravitationally powerful waves that the theory predicts must form as a disk tears itself apart. Even more tantalizing, nestled within one of these spiral arms, astronomers spotted a bright, compact clump. This lump of concentrated material, glowing brightly in the radio waves, is precisely where a model of disk instability would predict a new planet should be pinching off from its spiral arm. It appears to be a protoplanet caught in the very act of formation, a potential child of top-down collapse. Yet, the challenge of turning this tantalizing hint into definitive proof is immense. The great difficulty lies in confirming that this bright clump is a true, self-gravitating protoplanet, and not merely a transient knot of denser gas, a cosmic mirage that will eventually dissipate back into the disk. A density wave can look very similar to a forming planet in a single snapshot. The key is to watch it over time. A true protoplanet, bound by its own gravity, will maintain its identity. It will move along its orbit around the star, a solitary traveler on a predictable path. A simple density wave, however, is a pattern, not an object. It is like a wave in the ocean. Its shape moves, but the water itself does not travel with it in the same way. If observations over several years show this clump in AB Aurigae is indeed orbiting the star as a cohesive body, it would be the strongest evidence yet that we are witnessing disk instability forge a new world before our eyes. This is the new frontier of astronomy, using time itself as a tool to distinguish a true planetary birth from a fleeting ripple in the fabric of a cosmic disk. While ALMA maps the grand architecture of dusty disks, a new observatory is turning its gaze to the hidden hearts of these stellar nurseries. The James Webb Space Telescope operates as a revolutionary infrared eye in the sky. Its greatest power is its ability to see the heat signatures of the universe, allowing it to peer directly through the thick, obscuring veils of dust that block visible light. For the first time, we are not just looking at the silhouettes of protoplanetary disks, we are sensing the warmth of the planets being born within them. This shift from mapping structure to detecting thermal emission changes everything in the hunt for disk instability. A young, puffy protoplanet born from a top-down collapse would be incredibly hot, glowing fiercely in infrared light as it radiates the immense heat of its violent formation. Webb is perfectly designed to hunt for these specific thermal fingerprints. It can isolate the faint, warm glow of a nascent gas giant from the overwhelming brightness of its parent star, probing the very regions where core accretion struggles and disk instability is predicted to thrive. Early observations are already hinting at the chaos within. Webb has studied systems like HL Tauri, a star famous for its intricately ringed disk. While those rings suggest the presence of young planets carved out by core accretion, Webb's infrared vision has also detected surprising amounts of complex carbon-based molecules like benzene in the disk's cold outer regions. This is a region where the traditional model would expect simple ices to dominate. The presence of such complex chemistry so far from the star could be a clue that the disk environment is more dynamic and violently mixed than we thought, a potential signature of the large-scale gravitational stirring that disk instability would cause. The true smoking gun, however, remains just out of reach. The ultimate confirmation would be to catch a young giant in the act, not just as a clump in a spiral arm, but as a distinct, self-luminous world. Webb has the sensitivity to do this. Its future targets include systems like PDS-70, where we know two young gas giants are actively accreting material within a wide gap in their disk. By analyzing the specific wavelengths of infrared light coming from these planets, Webb spectrographs can dissect their atmospheric composition. A planet formed via disk instability might carry a distinct chemical signature, perhaps a composition that closely mirrors the raw gas of the protoplanetary disk itself, since it collapsed directly from it without the long, selective buildup of a rocky core first. Finding such a primordial atmosphere around a distant, massive world would be the most compelling evidence yet that the universe builds its giants from the top down. We are on the cusp of seeing not just how planets look, but how they are truly made. The universe seems to delight in creating planetary systems that defy our expectations. While our own solar system appears orderly, with small rocky worlds close to the sun and gas giants further out, telescopes have revealed a menagerie of cosmic oddballs that the classic core accretion model struggles to explain. These exotic systems are where the theory of disk instability finds its most compelling real-world evidence. Consider the star system HR 8799, located about 130 light-years away. Here, astronomers have directly photographed not one, but four colossal gas giants, each one far more massive than Jupiter. They orbit their star at staggering distances, with the farthest world taking more than 400 years to complete a single lap. In this remote, frozen realm, the protoplanetary disk would have been incredibly sparse. For core accretion to build such behemoths so far from their star would be like trying to construct a skyscraper in the middle of an empty desert with only a handful of sand. The process would be impossibly slow. The existence of this entire family of distant giants points powerfully toward a different origin, a rapid top-down collapse of a gravitationally unstable disk that forged all four worlds in a single dramatic event. Other systems show different but equally telling scars of a violent past. We have discovered planets on wildly eccentric orbits, tracing long, oval paths around their stars instead of neat circles. Some worlds are dramatically tilted, orbiting at a sharp angle to their star's equator, or even moving backwards. How does a planet end up on such a strange path? In the relatively gentle process of core accretion, planets tend to form in a flat, orderly disk and usually stay there. But a solar system born from disk instability is a chaotic and crowded nursery from the very beginning. The sudden, simultaneous birth of multiple massive clumps creates a gravitationally volatile environment. These young giants can violently tug and pull on each other, scattering siblings into bizarre orbits, ejecting some entirely into the darkness or sending others careening inward. The strange orbital architectures we see today could be the fossilized records of this initial cosmic chaos. These planetary oddballs force us to confront a humbling possibility. Our own tidy solar system, the only one we have ever called home, might not be the standard model for the galaxy. It could be the exception, a quiet suburban neighborhood in a cosmos filled with far more extreme and dynamic systems. Disk instability provides the crucial framework for understanding this broader cosmic diversity. It is the key that helps us explain the giants in the distant darkness and the worlds that dance to their own erratic rhythms, painting a picture of planetary formation that is far more inventive and far more violent than we ever dreamed. The very chemistry of a star may hold the secret to how its planets are born. This clue lies in a property called metallicity, which is simply the abundance of elements heavier than hydrogen and helium found in a star. These heavier elements, which astronomers call metals, are the building blocks of dust grains and rocky material. This chemical fingerprint provides a powerful way to test our two competing theories of planet formation. Think of it as a cosmic preference where the available ingredients determine the recipe. Core accretion is a process that thrives on solid material. It needs vast amounts of dust and ice to patiently build those initial rocky cores. A star with high metallicity, rich in these heavier elements, provides a perfectly stocked workshop for this bottom-up construction. Its protoplanetary disk is filled with the microscopic bricks and mortar needed to build planets from the ground up. This explains a fascinating pattern we see in our own galaxy. Stars that host known rocky planets often have higher metallicities than stars with no detected planets. The material was simply there, ready to be used. But what about a star that is metal-poor, one that formed from primordial gas with very little contamination from heavy elements? Its disk would be rich in hydrogen and helium, but lacking in the dust required for efficient core accretion. This is where disk instability finds its ideal environment. Without a lot of solid material to help the disk cool and clump in small ways, the entire structure remains massive, cool, and gaseous. The key to triggering the top-down collapse is the ratio of the disk's mass to the star's mass. In a metal-poor system, the disk can still be massive with gas, even while being dust-poor. This creates the perfect imbalance, making it far easier for the disk's own gravity to overwhelm internal pressure and spiral into instability. A gas giant can then form directly, bypassing the need for a dusty core altogether. This connection creates a clear and testable prediction for astronomers. If disk instability is a real and common process, then we should begin to find gas giant planets orbiting stars with surprisingly low metallicity. These would be stars that, according to the core accretion model, should not have been able to form such worlds at all. Every new planet discovered around a metal-poor star is therefore a potential vote for the top-down method, a giant born not from dust but from the raw collapse of a gaseous disk. This chemical clue turns every stellar spectrum into a historical record, telling us not just what a star is made of, but how its family of planets came to be. The very soul of a planet, its internal fire and chemical heart, is forged in the crucible of its birth. How a world is assembled leaves a permanent geological fingerprint, a hidden history written in its core and atmosphere. The fundamental difference between our two formation stories creates planets that might look similar from the outside, but are built from entirely different blueprints on the inside. Think of it as the difference between building a house from the foundation up versus inflating a giant, complex structure all at once. The final building may serve the same purpose, but its internal supports and material composition are worlds apart. This distinction becomes starkly clear when we peer into the heart of a gas giant. In the core accretion model, the entire planet is built around a massive, dense core of rock and metal, a seed perhaps 10 times the mass of Earth. This core acts as the planet's anchor, its gravitational center of gravity and primary source of internal heat from radioactive decay. For a planet born from disk instability, however, that story changes dramatically. This world forms from a top-down collapse of a large volume of gas. There is no requirement for a massive, pre-existing rocky core. Any solid material is incorporated as a fine dust that slowly rains down to the center over millions of years. The result could be a planet with a much smaller, diffuse core, or perhaps no distinct core at all, instead having a gradual increase in density all the way to the center, like a cosmic onion with no central pit. This single architectural difference has profound consequences. A planet's magnetic field, for instance, is often generated by a dynamo effect, the churning of electrically conductive material deep in its interior. For a gas giant, this usually means a layer of metallic hydrogen under immense pressure, but the presence and size of a solid core can dramatically alter that dynamo. A large central core might focus and strengthen the magnetic field, creating a powerful, structured magnetosphere like Jupiter's. A coreless planet, or one with only a dilute slurry of heavy elements at its center, might generate a weaker, more disorganized magnetic field, leaving it more vulnerable to the harsh stellar winds from its sun. The internal heat flow is another telling signature. Core accretion planets retain the intense heat from their formation, but they also gain a powerful, long-lived furnace from the radioactive elements locked in their large rocky cores. A disk instability planet, while born hot from the violent energy of collapse, lacks this substantial radioactive heart. It might cool down much more rapidly over its lifetime, its internal fires fading faster without that central engine. This cooling rate directly influences the planet's weather, storm systems, and its very appearance. These internal differences ultimately express themselves in the planet's atmosphere, the only part we can directly observe from light years away. The atmospheric chemistry becomes a cosmic diary. A planet formed by core accretion might have an atmosphere that is enriched in heavier elements. This is because the process of slowly accreting gas onto a massive core can be selective, allowing certain molecules to be trapped more efficiently than others. Its atmosphere might not perfectly mirror the raw composition of the protostellar disk. In contrast, a world born from disk instability collapses directly from a large swath of that disk. Its atmosphere should be a nearly pristine sample of the primordial disk gas, a perfect fossil record of the solar system's original ingredients, with a chemical composition that closely matches its host star, particularly in the ratios of key elements like carbon, oxygen, and nitrogen. This is where the James Webb Space Telescope transforms from an observer into a cosmic archaeologist. Webb's powerful spectrographs do not just take pictures of exoplanets, they dissect the very light that filters through their atmospheres. By analyzing the unique fingerprint of which colors of infrared light are absorbed, scientists can determine the atmosphere's chemical makeup with incredible precision. The dream is to compare the atmospheric composition of a distant gas giant directly to the spectrum of its host star. If they match almost perfectly, it would be a powerful clue that the planet formed via disk instability, capturing a snapshot of the disk's raw material. If the planet's atmosphere shows significant enrichment or depletion of certain elements, it would point toward the more complex, selective history of core accretion. We are on the verge of not just finding new worlds, but of reading their birth certificates, of uncovering the violent or patient stories of how they came to be from the secrets held in their alien air. A planet's birth story does not end with its own creation. It sets the stage for an entire family of worlds, for the moons that will circle it in the dark. We know how our own Jupiter's large moons, like Europa and Ganymede, likely formed. In the core accretion model, as the young Jupiter grew, it was surrounded by its own swirling disk of gas and dust, a miniature version of the solar system itself. Within this circumplanetary disk, dust grains coalesced, building the large, icy moons in an orderly procession, a small-scale echo of planet formation. But what happens when the parent planet itself is born from chaos? If a gas giant forms via disk instability in a single, violent collapse, how does that change the recipe for its lunar companions? The very method of the planet's birth dictates the nature of its cosmic household. When a planet is born from the top-down fragmentation of a spiral arm, it begins its life as a vast, extended clump of gas. This initial structure is not a neat, dense sphere. It is a massive, puffy envelope, a tempest in its own right. Within this churning, self-gravitating blob, secondary instabilities could easily arise. Think of a massive storm cloud on Earth where smaller vortices can spawn tornadoes. In a similar way, the collapsing protoplanet itself might experience its own internal gravitational turmoil. Denser pockets within the gas could potentially pinch off, forming smaller, self-bound objects directly from the planet's primordial substance. These would not be moons built patiently from dust, but siblings born from the same chaotic womb, potentially explaining the origin of some of a gas giant's largest satellites. Yet this violent beginning might also lead to a more impoverished lunar system. The rapid formation of the planet means there may not be a long-lived, stable circumplanetary disk from which moons can steadily accumulate. The raw material for moons is either incorporated directly into the planet during its initial collapse, or it is scattered away by the gravitational shock waves of the planet's birth. A top-down giant might therefore be a lonely wanderer, a solitary monarch without a large court of icy moons, or it might possess only a few large moons that formed alongside it in that initial burst, rather than a diverse collection built over eons. This adds a profound new layer to our search for alien worlds. The presence or absence of a complex lunar system around a distant gas giant could be a clue to its very origin. A giant planet with a rich, structured system of large moons might point toward a more orderly core accretion past, but a massive world, alone in the darkness or accompanied only by a few large, irregular satellites, could be a silent testament to a violent top-down birth. The story of moons is inextricably linked to the story of their parents, and by reading the lunar archives, we may finally decode the hidden history of the giants themselves. The serene orbit of a newborn planet is often just the beginning of its story. A world does not simply form and remain fixed in place. It can embark on a grand journey across its solar system, a process known as planetary migration. This movement is driven by a delicate gravitational dance with the very disk of gas that gave it birth. As a young planet plows through this dense gas, it creates spiral waves of density ahead and behind its path. Think of a heavy boat moving through water, creating a wake that pushes back on the vessel. In space, this gravitational wake exerts a torque on the planet. The intricate interplay of these forces can either sap the planet's orbital energy, causing it to spiral inward toward its star, or add energy, pushing it further out. For any planet, this is a precarious journey, but the speed of its birth dramatically alters its fate. A gas giant forged by the slow process of core accretion has a very different migration experience compared to one born in the violent instant of disk instability. The core accretion planet forms gradually, its gravitational presence growing slowly over millions of years. It begins its migration as a relatively small object, interacting gently with the gas disk, and its inward spiral can be a slow, stately procession. But a planet born from disk instability enters the scene fully formed, a massive gravitational heavyweight from day one. Its sudden appearance sends powerful shockwaves through the protoplanetary disk. This immediate and immense gravitational pull can trigger a much more rapid and dramatic migration. The type of migration a planet undergoes depends heavily on its mass and the local conditions of the disk. One common path is type I migration, which affects smaller, Earth-sized planets. They are like small pebbles in a stream, easily swept along by the flow of the gas. But for giant planets that clear a wide gap in the disk around their orbit, the more powerful type Roman II migration takes over. Here, the planet's gravity is so strong it carves a trench in the gas, and its movement becomes locked to the viscous evolution of the entire disk itself, like a massive log carried by a river's current. This is where the origin story of a planet writes its travel itinerary. A top-down giant with its immense initial mass can immediately begin type Roman II migration. Its journey is not a gentle drift, but a decisive and fast-paced march. This offers a compelling explanation for one of the great mysteries of exoplanets, the existence of hot Jupiters. These are gas giants that orbit breathtakingly close to their stars, completing a full orbit in just days. For a slow-forming core accretion planet to end up so close to its star is problematic, as it would have to migrate across the entire inner solar system without falling in. But for a disk instability planet, a rapid, early migration provides a clear and violent path. It could be born in the cold outer disk and then, within a short window of time, be dragged inward by the gas, parking itself in a scorching close orbit. Not every instability-born giant suffers this fate, however. Some might form at the very outer edge of the disk, where there is simply not enough gas left to exert a significant pull, leaving them stranded on distant, cold orbits as lonely sentinels. Others might form in a disk that is quickly dispersed by the young star's radiation, cutting the migration short and freezing them in place. The incredible diversity of planetary orbits we see today, from searing hot Jupiters to frozen, distant giants, could be the direct result of this chaotic interplay between a planet's rapid birth and its subsequent journey through the celestial currents of its youth. The serene ballet of a single star and its disk is just one possibility in a chaotic galaxy. Many stars are born in pairs, locked in a gravitational dance that transforms their planet-forming disks into cosmic war zones. In a binary system, the gentle pull of a single star's gravity is replaced by a constant, disruptive tug of war between two stellar siblings. This creates an environment of immense turbulence where the disk is stretched, compressed, and heated by the relentless gravitational forces. For decades, astronomers believed this stellar chaos would be a death sentence for planet formation, shredding disks before planets could ever coalesce. Yet, against all odds, we have found planets orbiting double stars like the famous Kepler-16 system, a real-world Tatooine. Their existence in such a hostile nursery forces a radical rethinking of how worlds are born. The very violence of a binary star might not prevent planet formation. It might simply demand a faster, more brutal method. This is where disk instability finds its most extreme proving ground. The gravitational perturbations from a companion star do not just stir up trouble, they can actively enhance the conditions needed for a top-down collapse. A passing stellar companion can push and pile up vast amounts of gas at the outer edges of a disk, dramatically increasing its local mass and density in specific regions. It acts like a cosmic plow, shoving material into a concentrated wave. This sudden injection of mass can be the final push that sends a disk over the critical threshold of the Toomre Q parameter, triggering gravitational instability where it might not have occurred otherwise. Furthermore, the constant stirring prevents the disk from settling into a calm, uniform state. It keeps the disk dynamically cool in a gravitational sense by preventing the smooth distribution of material that would otherwise provide stability. The result is a disk that is perpetually on the edge, primed for the rapid fragmentation that disk instability provides. In the turbulent cradle of a binary star, the slow and steady process of core accretion faces near insurmountable challenges. Dust grains trying to stick together are likely to be shattered by violent collisions or sent on chaotic paths that prevent steady growth. But disk instability operates on a scale that can withstand the turmoil. It forges a planet in a single, swift event, a gravitational fist punching through the chaos to create order. The presence of a gas giant in a system like Kepler-16 is not a paradox, it is a signature. It points to a formation story written not in patient dust, but in the violent collapse of a disk that was molded and manipulated by the dance of two suns. But what about the smaller worlds, the ice giants and the massive rocky planets that fill our galaxy? Could the violent process of disk instability, known for forging gas giants, also be responsible for creating these more modest worlds? This question pushes the theory into its most speculative yet fascinating frontier. The core idea remains the same. A disk becomes gravitationally unstable and fragments. However, the outcome of that fragmentation might not always be a colossal ball of hydrogen. The final product depends critically on the mass and temperature of the collapsing clump itself. Imagine a spiral arm beginning to pinch off, but this time the pocket of gas is not quite massive enough, or it is a bit too warm. Its self-gravity is strong enough to hold it together initially, but not powerful enough to pull in and retain a vast, lightweight atmosphere of hydrogen and helium. This could result in a failed instability, a clump that contracts into a dense world dominated by heavier elements, an ice giant like Neptune, or even a super-Earth, a rocky planet many times the mass of our own. The raw materials are all there in the disk: water, ammonia, methane, and silicate dust. A smaller, cooler fragment could easily incorporate a much higher proportion of these ices and rocks relative to hydrogen gas, sculpting a very different kind of planet from the top down. Another pathway involves the stars themselves. Disk instability is not exclusive to massive stars with massive disks. a low-mass star, a dim red dwarf, could still be surrounded by a relatively hefty disk. If that disk is cool and dense enough, it too could cross the threshold into gravitational instability. But around a small star, the entire disk has less total mass. The spiral arms that form would be less grandiose, and the fragments they spawn would be correspondingly smaller. Instead of Jupiter-sized behemoths, this environment might be a factory for Neptune-sized ice giants or large super-Earths, born directly from the disk's collapse without a lengthy core-building phase. This possibility elegantly solves another exoplanet puzzle. We have found countless super-Earths and mini-Neptunes orbiting very close to their stars. For core accretion to build such a massive rocky planet so near to a star is challenging, as the fierce stellar winds should blow away the light gases before a large core can form. But if these worlds were born as dense, gas-poor fragments in a top-down collapse, their existence suddenly makes much more sense. They are the smaller children of instability, worlds that never grew into giants, forever preserving the compact, heavy, element-rich nature of their violent birth. While this extended role for disk instability is still a hypothesis, it opens a universe of possibility, suggesting the top-down recipe might be a universal cookbook for planets of all sizes, from the smallest rocky world to the largest gas giant. These digital laboratories are where the theory of disk instability is truly put to the test. Unlocking the secrets of this violent planetary birth requires more than just equations on a chalkboard. It demands a virtual universe meticulously crafted inside the world's most powerful supercomputers. Researchers are running colossal three-dimensional hydrodynamical simulations, which is a technical way of saying they are creating a perfect digital twin of a swirling protoplanetary disk. The goal is to pour in the raw ingredients, the laws of physics, and then press play to watch what unfolds over cosmic time. The computational challenge is staggering. The simulation must account for the relentless pull of gravity on every single parcel of gas, the complex fluid dynamics of a whirling vortex, and the crucial effects of radiation as the gas heats and cools. All of these forces interact in a chaotic ballet, and tracking them across thousands of years of evolution requires trillions upon trillions of calculations. Pioneering groups like those at the University of California, Berkeley, and Princeton University have been at the forefront of this computational quest. Their work reveals how these digital experiments have evolved. The earliest simulations started with simple, smooth disks and basic physics. They proved that spiral arms could form and fragment, a crucial first step. But the real breakthroughs came as the models grew more sophisticated. Today's state-of-the-art simulations incorporate the twisting influence of magnetic fields, which can transport energy and angular momentum, dramatically altering the disk's stability. They now include detailed chemical networks tracking how molecules form and break apart, which influences how efficiently the disk can cool. A disk that cools too quickly can shatter into too many small clumps, while one that stays too hot might never fragment at all. This incredible fidelity allows scientists to probe the exact conditions, the perfect recipe of mass, temperature, and rotation that tips a peaceful disk into a planet-forming frenzy. Watching one of these modern simulations is like witnessing a new solar system being born from pure mathematics. You see the initial disk, a serene, glowing platter. Then, like a phantom hand, gravity begins to sculpt it. The spiral arms emerge not as static drawings, but as dynamic, evolving rivers of gas. You can watch them ripple, interact, and finally, in a climactic moment, pinch off into distinct, self-gravitating clumps that the computer now tracks as individual protoplanets. Each of these digital discoveries is a piece of the puzzle, helping us understand not just if disk instability can happen, but precisely when and where in our galaxy it does. Every revolutionary idea must face its skeptics, and disk instability is no exception. critics of this top-down model raise a crucial and valid point. What if these newborn clumps are simply too fragile to last? The initial collapse of a spiral arm generates an immense amount of heat, and this thermal energy can be a planet killer. A puffy, hot clump of gas has high internal pressure, which pushes outward, fighting against the inward crush of its own gravity. If the clump cannot cool down quickly and efficiently, that outward pressure will win, causing the entire structure to expand, unravel, and simply dissipate back into the disk from which it came. It would be a cosmic stillbirth, a planet that flickered into existence for a brief moment only to vanish without a trace. This is the fundamental survival challenge for any world born from instability. The critics argue that for a clump to survive, the disk must radiate away this heat with incredible speed, a condition that might be too specific and rare to make disk instability a common pathway. They contend that the window of opportunity is vanishingly small, a fleeting moment in a disk's multi-million-year life where mass, temperature, and cooling rates all align perfectly. In this view, our own solar system with its orderly planets is the norm, and the exotic giants found by our telescopes are the rare outliers perhaps formed by other, even more exotic processes we have yet to understand. Yet proponents of disk instability are not swayed. They have turned to their most powerful tool, increasingly sophisticated supercomputer simulations, to meet this challenge head-on. These are not the simple models of the past. They now incorporate the complex physics of radiative transfer, simulating how heat energy actually moves through the swirling gas and dust. The results are revealing a path to survival. The dust itself, long seen as the key player in core accretion, turns out to be a potential savior for top-down planets as well. When a spiral arm fragments, it traps within it countless microscopic dust grains. These solid particles are incredibly efficient at radiating heat away. As the clump contracts, this dust acts like a cosmic coolant, a blanket that wicks away the intense thermal energy from the collapse and releases it into space. This rapid cooling allows the clump to lose its supporting pressure, enabling gravity to gain the upper hand and continue the contraction into a stable, bound object. The simulations show that under the right conditions, this process is not only possible but robust. A clump that successfully cools can contract dramatically, increasing its density by orders of magnitude and solidifying its existence in just a few thousand years, crossing the point of no return long before it has a chance to dissipate. The debate over how common these conditions are continues to rage, but with every advance in computational power, the case for disk instability grows stronger, suggesting that the violent birth of a giant planet may not be a rare cosmic fluke, but a regular and breathtaking occurrence in our galaxy. The ultimate test for any theory lies not in our computers but in the stars themselves. The next generation of astronomical observatories now being built are designed to deliver the forensic evidence we need to finally settle the great planet formation debate. These are not merely incremental upgrades, they are revolutionary instruments that will transform faint hints into definitive data, allowing us to witness the birth of planets with a clarity we have only dreamed of. The Nancy Grace Roman Space Telescope, slated for launch later this decade, will be a powerhouse for direct imaging. Its advanced coronagraphs will act as an ultra-precise thumb, blocking out the blinding glare of host stars to reveal the faint, reflected light of orbiting gas giants. Roman will conduct vast surveys, scanning star-forming regions to take a cosmic census of young planets. It will find these worlds not just as single pixels, but as resolvable dots, allowing us to measure their orbits and precisely determine their masses. This data is crucial because it will tell us exactly how many massive planets exist at great distances from their stars, the very region where disk instability is predicted to be the dominant formation mechanism. A solar system crowded with distant giants would be a powerful vote for top-down formation. Following closely behind, the ground-based European Extremely Large Telescope, or ELT, will peer into the atmospheres of these alien worlds. With a primary mirror spanning an astonishing 39 meters, this colossal telescope will collect more light than any optical instrument ever built. Its suite of high-contrast spectrographs will dissect the faint glow of exoplanets with breathtaking precision. By analyzing the specific wavelengths of light absorbed by a planet's atmosphere, the ELT can determine its chemical composition molecule by molecule. The key test will be to compare this atmospheric makeup directly to the spectrum of its host star. If they match almost perfectly, it suggests the planet formed rapidly from a chunk of the disk, just as disk instability predicts. If the planet's atmosphere is enriched with heavier elements, it points toward the slower, more selective process of core accretion. The most ambitious future technologies, however, look beyond single telescopes altogether. Scientists are designing next-generation space interferometers. This concept involves flying multiple telescopes in a precise formation, millions of kilometers apart, and combining their light to create a virtual observatory with the resolution of a single, impossibly large dish. Such an instrument will be capable of something truly extraordinary, directly imaging the spiral arms and fragmenting clumps within protoplanetary disks around young stars. We would no longer be inferring the process from computer models or studying its aftermath. We would be watching it happen in real time, seeing the gravitational instability theory play out before our eyes. These observatories will also allow us to study planetary systems in their infancy, just a few 100,000 years old. This is the critical period when the disk is still rich with gas and the clock is ticking on planet formation. By capturing these young systems, we can see which method is active and under what conditions. The combined power of these missions will provide a multi-pronged attack on the mystery. We will know where the giant planets are, what they are made of, and how they are being born. The debate between bottom-up and top-down planet formation is rushing toward a moment of profound discovery, a time when the data will speak with a clarity that no theory can ignore. The existence of life on a small, rocky world may depend entirely on the violent birth of a distant giant. This is the profound connection between disk instability and our search for alien life. The way a gas giant forms does not just create a planet, it engineers the entire architecture of its solar system with fateful consequences for habitability. In one scenario, a gas giant forged by top-down collapse in the outer system can become a celestial guardian. Anchored far from the sun, its immense gravity acts as a defensive shield for the inner planets. It relentlessly perturbs the orbits of icy comets and rocky asteroids from the outer reaches, either flinging them harmlessly out of the system entirely or drawing them in to collide with itself. A world like Jupiter in our own solar system is thought to have played this protective role, potentially clearing the inner system of destructive projectiles and allowing life on Earth a more stable environment in which to emerge and evolve. A system where disk instability quickly places a massive sentinel in the outer darkness could therefore be a prime candidate for nurturing life on its inner terrestrial worlds. Yet the same formation process holds a terrifying alternative. If disk instability triggers rapid planetary migration, the consequences for habitability are catastrophic. A newly born giant planet embarking on a fast-paced journey inward is not a graceful traveler, it is a wrecking ball. Its gravitational wake would violently stir up the entire inner planetary system, scattering the building blocks of rocky planets or ejecting nascent worlds entirely. A potential Earth-like planet forming in the habitable zone, the region where liquid water can exist, could be flung into a deep freeze or a scorching orbit, or cast out into the interstellar void as a lonely rogue planet. The very mechanism that builds a giant world could simultaneously destroy the delicate conditions needed for life to ever take hold. This stark duality forces us to look at every new exoplanet discovery not just as a world, but as a clue to its system's turbulent history. When we identify a distant solar system, one of our first questions must be about the origin of its largest planets. Did they form quickly and violently, or slowly and patiently? The answer helps us assess that system's long-term stability. A system with a calm outer giant that likely formed via core accretion might be a promising, stable place for life. But a system showing signs of a top-down birth, with planets on eccentric orbits or a missing inner terrestrial belt, might tell a story of past chaos, a history too violent for fragile biology to survive. Our own pale blue dot may owe its existence to the specific, quiet way our Jupiter was born, a gentle giant in a calm nursery rather than a product of celestial upheaval. Science fiction has always raced ahead of science, building worlds from the faintest glimmer of a theory. The dramatic notion of disk instability offers a treasure trove of narrative potential, a way to imagine solar systems far stranger than anything we have yet found. Picture a civilization living on a moon orbiting a gas giant that is, in cosmic terms, still an infant. Their primary world is not a serene, ancient sphere, but a roiling, turbulent body, glowing fiercely with the residual heat of its violent birth just a few 100,000 years ago. The very sky above them is a constant, dynamic spectacle, shimmering with intense auroras generated by the planet's still-forming magnetic field. For these people, the concept of a stable, billion-year-old universe would be a foreign philosophical concept because their entire reality is shaped by a system still in its fiery, tumultuous youth. Their mythology might not speak of gods creating worlds in 7 days, but of a single, chaotic moment of celestial fragmentation that birthed their sun and their parent planet simultaneously. This changes everything about their culture, their technology, and their understanding of their own place in the cosmos. Their astronomy would be the study of an active construction site, not ancient ruins. They might even live in fear of their own planet, watching for new storms or gravitational shifts that signal its ongoing contraction. Another story could unfold on a world that was itself born from a smaller-scale instability, a super-Earth that condensed directly from a collapsing spiral arm. This planet would have a truly alien geology, perhaps lacking the distinct layered structure of a world built by core accretion. Its interior might be a homogeneous, seething mass of rock and metal, still settling and differentiating, leading to constant planet-wide volcanic activity. The very ground beneath the feet of its inhabitants could be young and unstable, with continents reforming over centuries rather than millennia. What kind of life would evolve in such a transient, violent environment? Perhaps a species with a cultural focus on impermanence and adaptation, their history measured in rapid, catastrophic cycles of destruction and rebirth. The idea also fuels darker narratives. Imagine a generation ship from Earth, traveling for centuries to reach a promising star system, only to arrive and find it is not the stable haven they were promised. Instead, it is a celestial battlefield with multiple young gas giants on chaotic, migrating orbits, violently scattering asteroids and planetary embryos across the system. The habitable zone is a shooting gallery, making any hope of colonization a deadly gamble. This scenario transforms the discovery of disk instability from an academic curiosity into a matter of survival, a cosmic warning that the galaxy is filled with young, dangerous systems that are anything but hospitable. These stories do more than just entertain. They use the creative lens of fiction to explore the profound implications of a scientific theory, helping us grasp the sheer power and diversity of planetary formation. They remind us that our own peaceful solar system might be a rare sanctuary, and that the universe is capable of forging worlds in ways we are only beginning to understand. So we are left with two grand cosmic blueprints for building a planet. On one hand, there is the patient, bottom-up craftsmanship of core accretion, a slow assembly from dust to pebbles to a mighty world. On the other, the explosive top-down artistry of disk instability, a swift collapse that forges a giant in a cosmic blink. This is not merely an academic debate, it is a fundamental question about the diversity of worlds across our galaxy. The evidence for this faster, more violent path has steadily mounted, not from a single source, but from a convergence of clues. Supercomputer simulations show us the beautiful, inevitable dance of spiral arms fragmenting into protoplanets. Telescopes like ALMA capture real disks etched with those very same spirals, with bright clumps hinting at newborn worlds caught in the act. And the exoplanets themselves, the distant giants in frozen orbits and the planetary oddballs on wild, eccentric paths, serve as the ultimate testimony, challenging the old models and demanding a new explanation. The most profound realization is that we likely do not have to choose one story as the only truth. Our universe is a pragmatic and prolific builder, using every tool available. In one corner of a galaxy, around a star rich in heavy elements, the slow and steady process of core accretion might patiently construct a family of rocky planets. In another, around a massive, cool disk, the swift chaos of disk instability could rapidly assemble a court of gas giants. Our own solar system, with its clear division of small inner worlds and large outer ones, may simply be one possible outcome, one architectural style among countless others in the cosmic neighborhood. The search is no longer about which theory is right, but about understanding the conditions that favor one method over the other, painting a far richer and more spectacular picture of planetary birth than we ever thought possible. This grand cosmic debate is far more than a simple argument between two theories. It is a living, breathing example of how science truly works, a relentless tug of war between ideas that pushes our understanding of the universe forward. Our picture of the cosmos is never finished. It is constantly being challenged, refined, and sometimes completely rewritten by the very evidence we uncover. The birth of a planet is not a settled chapter in a textbook. It is a dynamic frontier of discovery. And the most profound realization is that this celestial drama is not confined to the distant past or to computer simulations. Right now, at this very moment, around young stars scattered throughout our galaxy, protoplanetary disks are swirling. Within those disks, gravitational forces are locked in their eternal struggle. Spiral arms may be coiling into existence, and clumps of gas could be collapsing under their own weight, igniting the birth of new worlds through top-down chaos. Or in a quieter corner of the same disk, dust grains are patiently sticking together, beginning the slow, bottom-up construction of a rocky planet like our own Earth. This ongoing creative process is happening everywhere, a silent, perpetual genesis of new solar systems. So the next time you find yourself looking up at a clear night sky, remember that you are not just looking at a static tapestry of distant lights. You are witnessing a cosmic construction zone of unimaginable scale. Each pinprick of light could be the home of a solar system with a story entirely different from our own. A story we are only just beginning to read thanks to eyes like the James Webb Space Telescope. We want to hear your story in this cosmic conversation. After this journey through the birth of giants, which path to planet formation feels more compelling to you? Do you find the patient order of core accretion more convincing, or the violent, rapid drama of disk instability? Share your thoughts in the comments below, and if you are hungry for more explorations into the frontiers of futuristic science and technology, be sure to subscribe. The universe has countless more mysteries waiting to be uncovered.